For many years, astronomers have searched the cosmos for planets that resemble Earth. Water vapor, a mild climate, rocky terrain, the ultimate wish list. But what if one of the most studied exoplanets ever contains almost everything on that list, yet turns out to be the worst place in the universe? 64 light-years away, in the constellation of Vulpecula, hangs a gas giant catalogued as HD 189,733b. From the very first data, it defied every existing model. They found it using the transit method. The idea is simple. The planet passes between its star and our telescope, causing the star's brightness to dip for a moment. Like a fly's shadow crossing a street lamp, only this fly is the size of Jupiter. This tiny drop in brightness let scientists measure the planet's size. Then, spectroscopy, breaking down the star's light into its components, revealed its mass. In other words, a single shadow told us more about this planet than years of direct observation ever could. And this is where things get strange. This planet belongs to a class known as hot Jupiters, gas giants roughly the size of our Jupiter, but orbiting their stars at distances that defy intuition. How close? About 1,000 times closer than Jupiter is to the Sun. In other words, it practically clings to its star. So close, a full orbit takes just over 2 Earth days. 2 days, that's 1 local year. While we have a weekend here on Earth, an entire calendar flips over there. Here's what's fascinating. This planet became one of the very first exoplanets where scientists managed to directly study its atmospheric composition. And the results, to put it mildly, were misleading. Water vapor, present. Carbon dioxide, present. Traces of methane, also there. It sounds almost familiar, almost Earth-like. On the surface, a typical chemical mix, nothing alarming. But then came hydrogen sulfide, the same gas that smells like rotten eggs, and in high enough concentrations, can kill within minutes. And that's not even the full list of challenges. Scientists still debate which processes create this cocktail at temperatures we'll discuss shortly. Water vapor and methane. 2 substances that, on Earth, signal life. Here, they meant something entirely different. The real mystery awaited astronomers when they finally tried to see what this world really looked like, and the color they found didn't match any known pattern. Sapphire. Deep, rich, flawless sapphire. That's the exact shade captured by the Hubble Space Telescope when it first measured the reflected light from this planet. Blue. So intensely blue that any astronomer at first glance experiences the same automatic reaction. Water. An ocean. Something familiar. That's how we're wired. Blue means Earth through a spaceship window. It's the Pacific Ocean on a globe. It's the very first thing a child notices when they see a photo of our planet from space. The brain makes this connection in a split second. Blue equals water. Water equals life. A simple, reliable chain shaped by millions of years. And here we have a planet 63 light-years away, and it's blue. Bluer than Earth. Here's the fascinating part. The water vapor previously detected in the atmosphere has nothing to do with this color. Absolutely nothing. The planet's blue tint isn't from oceans. It comes from light scattering off microscopic particles suspended high in the atmosphere. Simply put, the star's light passes through clouds made of something incredibly fine, and the shorter blue wavelengths bounce back toward us. What exactly are these particles made of? At temperatures soaring above 1,000 degrees Celsius, and even hotter on the day side, silicates in the atmosphere don't stay solid. They melt. Tiny droplets of molten glass form, each smaller than a micron. These droplets scatter the starlight, creating that deceptive sapphire glow we see. Glass. Liquid glass floating in the searing clouds. What once seemed like a distant cousin of Earth's oceans turned out to be a veil of molten silicates heated enough to soften solid rock. And this veil isn't just a striking feature. It hangs in the atmosphere, where the pressure difference between the day side and the night side is so extreme that the air can't stay still. The air on this planet can't just hang still. Literally, it can't. To understand why, we need to explore one key feature that sets this world apart from everything we're used to. This planet is locked in place. The gravity of its star, a yellow-orange dwarf slightly cooler than our Sun, has long since stopped it from spinning on its axis. More precisely, it's locked its rotation to match its orbit. This is called tidal locking. Simply put, the planet always shows the same face to its star, like the Moon does to Earth. But here, the consequences are completely different. One hemisphere basks in eternal daylight. The other remains trapped in endless darkness. On this planet, there's no dawn and no dusk. Never has been, never will be. Now, let's talk temperature. The dayside blazes at over 1,000 degrees Celsius. That's hot enough to make copper glow red and cause rock to lose its hardness. Starlight hammers down on the same spot without pause. Hours, years, even billions of years. Air on the dayside expands, grows lighter, and rises. On the dark side, the opposite happens. The atmosphere cools, contracts, and presses down. Between these two hemispheres, a monstrous pressure difference builds. And this is where things get truly fascinating, the part that makes understanding the mechanics worthwhile. The pressure difference between the blazing hot and dark hemispheres acts like a colossal atmospheric pump. Imagine opening a door from a steamy sauna into the freezing cold. The air would rush through the gap with enough force to tear the door from your hands. But here, the door is the boundary between hemispheres, stretching thousands of miles wide. And the air doesn't just move, it accelerates to supersonic speeds. Over 7,000 miles per hour, nearly 9 times faster than the speed of sound on Earth. Compared to that, a Category 5 hurricane with 300-mile-per-hour winds feels like a gentle breeze. And this wind carries a heavy load. Remember that sapphire glow? The tiny droplets of molten glass floating in the upper atmosphere, scattering light in the most beautiful way? They're not just drifting. A supersonic wind sweeps up these fiery silicate particles from the planet's dayside and flings them horizontally, skimming the surface toward the night side. Along with them, toxic gases, boiled out from deep within the atmosphere, race along. This isn't rain as we know it. Rain falls downward. Here, droplets of liquid glass shoot sideways, traveling fast enough that each one, just a fraction of a millimeter wide, carries the energy of a bullet. The entire planet acts like one giant aerodynamic tunnel, where molten glass takes the place of air. Yet the atmosphere fueling these storms isn't permanent. With every orbit around its star, the planet loses part of what it's made of, a slow, relentless process that's been unfolding for billions of years. Storms, glass-like rain, supersonic winds. These all seem like the main threats. But here's the strange part. The real killer works quietly. The star this gas giant orbits slowly devours its atmosphere. Scientists call this process atmospheric evaporation. Because the planet circles so close, its orbit is 13 times tighter than Mercury's, the stellar wind slams into the upper layers of its gas envelope, stripping away the lightest elements first. Hydrogen and helium vanish first, the very foundation holding up the planet's entire bulk. And that's where the scene gets captivating. The stripped gas doesn't disappear instantly. Instead, it stretches out, forming an extended cloud around the planet, a loose tail trailing along its orbit, like the tail of a comet. But it's not dust or ice. It's the guts of a dying world, pulled outward by the star's gravity. Now, let's leap forward. Hundreds of millions of years from now, if nothing stops the process, and there's nothing that can, the planet could lose its entire gaseous envelope, completely. All that would remain is a dense, rocky core, a charred remnant where a giant once was. At this point, it's worth answering the last question. Could anything alive survive in this hell, right now, while the atmosphere still lingers? The answer is simple. Daytime temperatures melt rock. No known biochemical process can endure such extreme conditions. There's no solid surface. This is a gas giant, with nowhere to anchor, no foundation for chemistry to build on, and the constant cataclysms, supersonic winds, pressure swings, thermal shocks, destroy even the faint hope of stability, the kind necessary for evolution to get a foothold. The planet is sterile, and yet it is already dying. But it's this very agony, captured by our instruments, that left behind something scientists never expected to find. What they discovered proved more valuable than any new element. The planet itself, with its glassy winds and melting skies, became a testing ground, a laboratory for refining techniques that let scientists break down the atmosphere of a distant world without ever leaving Earth. Every spectral fingerprint captured from this gas giant taught astronomers to read exoplanet chemistry with greater precision. Put simply, before searching for oxygen in the atmosphere of a potentially habitable world, they had to learn how to detect silicates in hell. And here, it's worth taking a step back and looking at the bigger picture. The universe didn't stop at just one kind of hell. At the other extreme lies TRAPPIST-1e, nestled in the constellation Aquarius. It's a rocky world, almost Earth's size, orbiting right in the habitable zone of its star. There could be liquid water there. Nearby, there's the super-Earth K2-18b, where scientists have detected traces of water vapor and methane in its atmosphere. Two worlds where, at least in theory, life's chemistry might take hold. Now, let's shift the focus the other way. WASP-76b. On its dark side, iron actually condenses and rains down as molten metal droplets. An iron rain. KELT-9b is even hotter. And between these extremes, between the hope for life and a shower of molten metal, stands our protagonist, the quintessential, ominous giant. But the scientists went beyond just analyzing the spectra. They took the data, the light curves, the frequencies of radiation, and transformed them into sound. This process is called sonification. Every frequency of light became a musical note. Every shift in brightness turned into a change in volume. The result isn't a recording of wind sweeping across a surface. It's not a microphone caught in a glass storm. It's mathematics translated into acoustic vibrations, the voice of raw data. Yet, when you hear this sound, deep, drawn out, with wavering overtones, it's hard to shake the feeling that it's a moan, that the planet, slowly stripped bare by its own star, is actually speaking, not in words, but in frequencies we've converted into our own language. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." HD 189,733b is not where we found life. It's where we learned how to look for it. And the sound, born from its data, stays with us, a reminder of how fragile the line is between a world where rain falls as water and one where it falls as glass. Silence. And within it, a single note drifting off into the darkness.